Thank you very much. Good morning, Matthias.
Good morning, Amanda.
Good morning, Mensch.
Sehr gut.
Good, welcome. Welcome to this morning session. This talk has the purpose of giving a proof within the context of synthetic algebraic geometry of Serre's criterion for affineness, which is the following theorem: that X be a scheme, then X is affine in case that it is cohomologically trivial, by which we could mean any of a couple of different things. For now, I would like to mean that the first cohomology of X with respect to any weakly quasi-coherent bundle of modules vanishes. Later on in Felix' talk, we will see the converse direction, that affine schemes are cohomologically trivial.
Already? For H1 we've already.
Awesome. Then we will then also see it for all others. In case you want to have a reminder of what WQC bundle of modules is, that we will have this reminder later. But in case you also want a reminder of what H1 is or what it means that this is zero, then let me give you the following equivalent characterization, namely every short exact sequence of WQC bundles remains exact after passing to global sections. So the global sections factor let me just write as follows. If this is a short exact sequence of weakly quasi-coherent bundles of R modules, then so is the induced sequence on global sections. Recall what's a bundle. A bundle is a family of R modules, one module for each point of X. And a map of bundles is a family of maps, one for each point of X. And such a sequence is exact if and only if it's individually exact for every point. Okay. This, by the way, is not a definition. Instead, it's a result. You write down the category of bundles, of WQC bundles, and then you observe that it's an abelian category, and then you simply check what exactness amounts to in that category. Okay, and these are global sections. So in type theoretic notation, this would be written as this. The set of dependent functions, the type of dependent functions, which map a point, lowercase x, in capital X, to some value in the xth component of the family M. Okay, so that's the criterion.
I don't understand the thing about being exact and pointwise being exact. Hugo, we had this example, I think, from the trivial line bundle to the trivial line bundle. On the affine line, the map that multiplies by x, the function x of the affine line. What was it? So this is not pointwise injected because at 0 is the zero function, it's not injected. Yes, but it is.
The mono, the appropriate category.
It is a monomorphism in the category of all R module bundles, or what?
Finitely presented
And
module bundles, I guess.
Okay, now Ingo is saying it is not a monomorphism in the category of weakly quasi-coherent.
No, it's also a morphism in that category. We checked at some point that the category of WQC bundles is full abelian subcategory of the category of all bundles. So kernels and co-kernels in that subcategory are computed exactly as in the larger category of all bundles.
Okay. And so Ingo, what do you say about this map? Do you think it's a monomorphism or not?
Well, I would claim that it's not a monomorphism.
Okay, which bundle do you write?
Because it is not the case that for all x this map is injective, because I can explicitly write down one x for which it is not injective, namely x equals 0.
Yes, very good. And all right, I can also see some bundle that can write to the left of it to see that it's not a monomorphism, namely the bundle that I want a bundle that has the fiber R at 0, and nothing everywhere else in some sense. And I think you have to take the sub-bundle of the constant bundle R of those points where either at the point x or at the point x equals 0 or the element of the bundle I'm looking at is 0.
You mean this one? I think I agree that this is a submodule of R. Okay. And and let's check that if we post-compose with that map, that we then obtain the 0 map.
Yes.
I think that's okay, because if we are given number A with that condition, then we know that A times X will for sure be 0, because one of its factors will be 0. Okay, and to conclude the demonstration that this morphism is not a monomorphism, we would need to verify that it is not the case that this is the 0 module.
That the inclusion is not the 0 map, right?
Okay, but the inclusion is not the 0 map. And
that's fine, right? And add 0 and map to something, and map the element 1 to 1, which is not 0.
Exactly.
Okay, so it is not a monomorphism in the category of all bundles, and now you say it's also not a monomorphism in the category of weakly quasi-coherent bundles because this E is weakly quasi-coherent, is it?
I don't even need to look at it to deduce that it is WQC, because it's a kernel of a map between WQC modules.
Okay, good.
And a nicer way to write this would be R to the x equals 0.
I think I agree. In case it's correct, which I don't think right now. So you wanted to write down this, right?
Yeah, because then it's apparent that it's
Yeah, but I'm doubting that.
okay.
So this is like a product, but this is like a sum.
Yeah, what do we need?
We want the x equals 0 index sum of R's properly.
We have this inclusion, let's call it I, and then this module here would be the push forward of the constant bundle on the point. Okay. However, this here, the E, is I think the I lower shriek. Okay. Of R. Something like that.
Okay, but to contrast the situation with the thing that you and I had in mind before, so it seems that this is a monomorphism of bundles of finitely presented modules. But it's not a monomorphism of weakly quasi-coherent bundles of weakly quasi-coherent modules. This seems to be the
You're claiming that in the full subcategory, which is not an abelian full subcategory, of finally presented bundles of modules, pointwise finally presented, that there it's a monomorphism?
yes.
Okay.
Yeah, I think I'm sure.
Okay, good.
Yeah.
Okay.
That's
Okay.
the claim.
Sorry. Yeah, sorry for the detour.
No, I liked it. Yeah. And also, perhaps as a comment to those of you who were not present in Göteborg last time, that result that the category of WQC bundles is a full abelian subcategory of the category of all bundles, that is quite important. And for a long time we were unsure like which category of modules to consider, which one is best. And I think right now it has settled a little bit to WQC models, which at least in my mind was a notion most strongly argued for by Felix.
I mean,
There are many
not
conditions.
that I think they are philosophically the right thing. It's just from the proofs about cohomology.
Yeah, so at some point we should drop the adverb
But
weak.
Yeah, and I think we should also just find a different word for them.
Yeah, I mean, we
Altogether.
don't really know what it is. I mean, you sometimes say things,
Yeah.
but I mean, for me, it doesn't connect to something classical yet.
Yeah, perhaps in the final minute of this talk, I will just write down the external semantics of WQC, just so that we have it on the board clearly and can discuss better about it. It's very important because this is an abelian category is very important because some results which we kinda had earlier, especially the Göteborg people had kinda earlier, really depended on the fact that we have an abelian subcategory. So that was really a crucial point. How will we prove the theorem? The idea is to employ a very standard criterion for affinities, namely the following. Let X be a scheme. If there are global functions f1 to fn from x to r such that firstly all those opens are affine. So that's the set of those points of x where fi of x is not 0. And such that in the ring of functions from x to r, those elements generate the unit ideal. Then x is affine. Okay, this notation here means that there are further functions g1 to gn such that the sum over the gi times fi equals 1.
Why units?
Not
absolutely.
Yeah. I'm always a little bit unsure whether I should write r to the x or whether I should write a1 to the x.
Yeah, I mean, here you use it as an algebra.
Mm-hmm. Yeah, that's a good argument. Yeah.
But it doesn't always work that you clearly know.
Yeah. I mean, that's also the beauty of it, right? That we are.
No, A1 is also an algebra. I think.
Yeah, but
Yeah.
it's more that it's an algebra object in the category of schemes, right?
Yeah.
But I think this is the same point as yesterday. So if you want to look at it as a space, It's A1.
Yeah.
If you want to look at it as a finitely presented module, it's R.
Yeah.
Finitely presented. Then it's R to the 1.
Well,
Right.
yeah, but it's still R. I mean,
Yeah.
So,
The algebra is R. As an algebra is R.
yes.
Okay. How to prove that remark? So it's not entirely straightforward if you have never seen the proof of the remark. However, it's also not technically demanding. In particular, all the standard proofs of that fact are already constructive, except for the fact that they are set in the context of the additional algebraic geometry, where the foundations are not laid out in a constructive manner, but the proof of that remark itself is fully constructive. If you have time, we can sketch it at the end, but because that's not the heart of the argument, I propose to skip that for now. Okay, so let's do a proposition. Let X be a scheme. If X is covertly trivial, then there are functions as in the remark. So that is how we will prove the theory. And here's the proof. Because X is a scheme, there is an open affine covering. Like that. Then, by the following lemma, which will constitute the heart of the argument, we may assume without loss of generality that all those ui are already of the form d of fi. I will write that down and let the lemma down in a second. By the following lemma, we may assume without loss of generality that the ui are of the form d of fi for some global functions fi from x to r. Because we have this. We kinda know that condition, but first, not in the ring of global functions, but just pointwise. Because that, for every x in x, 1 is an element of this ideal of numbers. I know that for the following reason. Given an arbitrary point lowercase x, that point is an element of capital X, and hence it's a member of one of the UIs. The UIs are by now in the proof exactly those d of fi. So fi of that point is not 0. So one of those generators of this ideal here is a unit, and hence in particular the ideal contains the unit. Okay, I'd like to do the jump up to the stronger result here, clause number 2 in the remark. And for that, we will again use the triviality condition. We will also use it in the lemma, in the following lemma, not yet stated, but we are also using it a second time here, namely as follows. In other words, the linear map or the morphism given in matrix notation by this expression is surjective at each component and hence also surjective on global sections by because X is cohomologically trivial. Let me explain a little bit more careful. So what is this bundle? That's the trivial bundle. Its values are at every point. So it can be called a constant bundle, which is why I put the underline there. So its component at a point x of capital X is just R.
So at each component means in the fiber over each point.
Yeah. Perhaps I should write fiber-wise instead of at each component.
Or at each point.
At each point both are better than what I wrote here. Yeah. What's this bundle? Well, that's also a constant bundle. And at the point X, the fiber is R to the n. Okay. So at each point we have a map from the vector space R to the n to the vector space R to the r1. That's given by a matrix, by a rectangular matrix, namely this matrix. And fiber-wise, it is surjective precisely because of that condition. We can write the unit element 1 here in the right as a linear combination of those fi's exactly thanks to that. Okay, and if we take global sections, then here we will have the ring R to the X. And the surjectivity expresses then exactly this condition. And perhaps the only thing left to remark here is how this cohomological triviality helps us here. If you want to be like very, very careful, then I would need to do the following. I observe that this is an epimorphism in the category of WQC bundles. Then I extend this to a short exact sequence by adding a 0 at the right and adding the kernel at the left. Okay, then I have a short exact sequence of WQC bundles. I apply global sections. I ignore the thing in the beginning with the kernel, and I just focus on the rightmost map, which is surjective because of the 0.
Well, in some sense, you can't forget about the kernel because you need the result of the kernel. With quasi-current.
Exactly.
So, I mean, the kernel is the most important thing.
Indeed, yeah. Indeed. From this point of view, yes, I agree. Yeah. One of the two results showing that the kernels or that coordinates are WQC again is harder than the other. I forgot which one. And at least one of those, I think both, requires a risky local choice. So it's really a non-trivial result. Okay. So we have criterion number, clause number 2 is satisfied, and that concludes the proof of this proposition. Okay, and now the question will be what was that lemma and how to prove that lemma, and that will be the core of the argument. I'll write on the lemma, and then you still have opportunity to ask questions regarding the proposition. Let X be a scheme.
So the assumption that X is cohomologically trivial was used already, but will be used again in that, right?
Right.
And so far you only used it to go from subjective points to subjective on global sections?
Yeah, right. And I will also never use it in any other way.
Okay.
So the lemma states the following. Let X be a scheme. Assume that it's cohomologically trivial. Assume that we are given a covering of X, a binary covering, where U is affine. Then there's a function f such that firstly d of f is contained in U and such that X is still the union of d of f with B. So that given U might not yet be standard open, but the statement of the lemma is that we can always shrink U to become a standard open, open of the form D of a global function. And we will still have that the union of D of f in B is all of X. So to be more precise, we are using the lemma in the proof of the proposition above, not once, but I think n times, or perhaps n minus 1 times, something like that. Because we are arranging that as U1 union some other open. Then we apply the lemma to obtain that U1 could also be written as D of some function f. And then we just use commutativity of union to put the next U2 at the very front. And then we use the lemma again and again and again until we have all n functions f1 to fn. Before we embark on the proof, let me just mention that d of f will again be affine. Because it's a standard open subset of an affine scheme.
A priori, f is defined on whole x and not on u,
Yeah.
but we don't care.
Yeah.
Is this part of the lemma, or does it follow only after the proposition?
The remark in parentheses follows just from the fact that U is affine, and yeah, that's it.
Oh, you are fine. There it is.
Yeah.
You said D affine, you did not say B affine.
Yeah. It was also important because in the application, I will, in the first step, declare this to be our V. And then later on, I will move the U2 to the front. And the U1, which has changed into a D of F1, to here. And then that will be V. And so on and so on. Okay. Then let's do the proof. who should be credited for that proof? Well, firstly, it should be the members of the traditional algebraic geometry community, from which this proof was inspired. And then more precisely, it should be perhaps credited to all the members of the synthetic algebraic geometry community, which contributed to a very nice atmosphere at the last meeting. And then if you want to be even more precise, this was a discussion mainly involving several people, but mainly Felix and David and myself. And the final proof step was offered by David 1 day later. Okay, proof.
I remember being a passive bystander. That's it.
It's 4 steps, all of them interesting in some sense. So let's start. First, observe there's a subset K of U which is closed in U, such that the complement of K in U is the intersection of U with V. This K will not be unique, but that won't matter. How do we know that such a K exists? U intersected with V is an open of U, right? So, as with any open of any affine scheme, this is a union of standard opens. That's a non-trivial result, which by nowadays is proven. It requires Zariski local choice, because the definition of what an open subset is a pointwise definition. A subset is open if and only if for every point of the superset, the condition that the point is contained in the subset is an open proposition. So for each point we have something, but from there it's a non-trivial step to obtain those functions defined on all of the affine scheme, on all of you. But you can read it up in the notes. Yeah.
So, can I ask, in a sense, this tells us that all the schemes that we see are falsely separated?
Yes. Yeah.
So you need Zariski local choice to prove that.
Yeah. So currently it's, I'd say, conscious design decision in synthetic algebraic geometry to define the notion of scheme in such a way that all the schemes are what is classically called quasi-compact and quasi-separated. That's, I think, for a couple of reasons. One is that's a philosophically rewarding notion. Everything is like finite in some sense. It's also nice because the connection with the external setting is particularly nice in that setting. And then thirdly, at least for quite some time, we just didn't know how to relax that requirement. We call in standard algebraic geometry, you say, well, a scheme is some kind of space, topological space, locale, topos, whatever, which has some covering by open affines. You might think that we can just mimic this definition in synthetic algebraic geometry. However, Matthias?
Hi.
Your standard remark?
What?
Propositions?
Proposition. Sorry, what?
The thing is, with that definition, every set whatsoever would be a scheme, because every set whatsoever can be written as a union of singleton sets. So, and these are definitely affine. Yeah. Perhaps not every set whatsoever, because that's not an open covering, okay? but at least if M itself is a subsingleton, if M itself is a proposition, we would have this would exhibit M as a scheme, and that's philosophically false, and it also does not correspond to an external fact. So we need to put some condition on that indexing family here. And the easiest one is to say, well, it should be finite. And nowadays, I think we also know more relaxed conditions. However, that has not yet been fully explored. Perhaps we should at some point.
I'm not sure whether I'm convinced about your statement that, that this example said that it's useless, I mean, to put no further conditions.
Yeah, I
mean,
want to put further conditions. We need to put further
No, if you don't put further, you mean you said if you don't put any further conditions, then more or less.
So what exactly our definition of open proposition is? It's an arbitrary union of the standard open propositions. Is that what we're talking about?
No, I mean.
Mm-hmm. Yeah, good point on this.
A notion is useless. I mean, not necessarily if it's not connected to classical algebraic geometry, because we know that for a subset of this notion, namely for quasi-coherent, quasi-separated schemes, we have a link. So as long as we can prove that some schemes that appear up in our construction proofs are of this type, then we know that we have classical results. I would say notion is useless if we cannot prove anything more interesting about it than we could prove about general types.
I think I missed the more general notion of scheme that we are.
But if we just say, we just drop the finiteness condition and don't add any further condition, then of course we can call this a scheme. And as long, and if we can do.
I think it just means that every set is a scheme.
Yeah, okay.
Okay.
That's not a, I mean, if we can do geometry over these type of things, then fine, why not? I mean, then.
Okay, but we don't need to make the definition. We can just say we take all sets. We don't have to.
Yeah, but then at some point we have troubles, and then whenever we need to find this condition, and so I think it's more like what we are looking for is a very nice category that includes all examples we need, and then then we should think of extending it if some constructions get out of this. Category. And I think it's not so clear. I mean, in classical algebraic geometry, we can go a long way with quasi-coherent, quasi-separated schemes. Right. And of course, one extension is to use, to drop this finiteness condition, and in some, sometimes they show up, but there are other directions, say, going in direction like the formal schemes or generating co-limits of schemes that are likewise generalizations that we can make. I mean, just because classically there's a very easy road dropping this quasi-coherent, quasi-separate condition does not mean that it's the only or the best route. So I would. Yeah, I mean, for example, yesterday we saw this P infinity. And so then we can ask whether we have some foundation, whether we have some right to call this a scheme, and what kind of scheme it is it, or maybe we would like to call this the inf scheme.
Yeah, but we still have, I mean, we still have to find a definition of that where P infinity fits in. I don't think you just want to define in synthetic algebraic geometry, we call any set an inf scheme, right? Because that doesn't capture what we know about P infinity.
No, my point was not that I would like to change the definition of scheme. I would stay with quasi-separated. I just wanted to argue about the reasoning why we don't want to.
Okay.
We could allow unions indexed by external sets. Standard opens.
That we could definitely allow, and thereby recover, using the model, the standard notion of schemes in algebraic geometry, traditional algebraic geometry. The only issue is that it's
Not an internal definition.
it's not a purely internal definition.
If we don't have geometric logic, but we don't have the processes.
Yeah.
But I mean, to really arrive at the standard notion, we would also have to drop the locally finite type, which we haven't talked about.
Yeah, that also, but I think for that,
And we have to use a different notion of open. I mean,
yes,
to do all those three things,
Yeah.
I would.
Yeah.
I need a reason.
Yes,
Like,
yeah.
Yeah, that's my point. I mean, if we
Yeah.
hit a wall,
Yeah.
then we have to see how go through or around it.
Okay, so what's the k then? We can take as k the vanishing locus of those functions g1 to gn. Okay, that will definitely be a closed subset of U. It might not be a closed subset of X. I'm not claiming that, but it's closed in U. It will definitely not be uniquely determined. You see that already from the fact that I could also add some powers here, and it would still work. I mean, here the D sets don't see any powers. And yeah, why is that condition satisfied here? So if you are given a point in U times V, then one of those G's is not 0. Hence, it's not the case that it's in K for which all the GIs would need to be 0, and vice versa. So we obtain such a subset. And then let I be the inclusion. Next, I will write down a bundle morphism, and I will claim that it's fiber-wise surjective, and then by cohomological triviality, we will conclude that it's surjective in global sections.
I'm a bit confused about how you build the K, because so you have an open, so you know that there merely exists G1, Gn.
Right, yes, yeah.
But what you want to build is not in a proposition.
Well, I'm just claiming the mere existence of such a subset.
Okay.
Yeah, yeah.
Okay.
Yeah. Okay. A certain bundle morphism, namely from J, I will introduce that, to the push forward of the constant bundle is fiber-wise.
What are we trying to prove? Is it not a proposition? When you say then there is a function f.
Yeah, I also mean merely. Should I, in this context, in this culture, write first and merely? Then they are merely.
How would you write purely? I wouldn't. Because you prove a proposition in the end, so. I don't know.
Affinity, yeah, affinities, yeah. Yeah. Okay, but it doesn't hurt to have it in.
Finitely many things which are only merely there.
Yeah. Okay, so what is that map, and more, and before that, what is the domain and what's the codomain? Okay, firstly, what is J? J is a certain bundle of ideals. One ideal for each point of X. And Jx contains all those numbers A such that A is only invertible in case X is an element of U. On first glance, this might look like a slightly weird ideal. Why are we concerned with that particular ideal? However, picture of what a global function, a global section of the bundle J would look like. That would be a function which reads an arbitrary point x, lowercase x of capital X as input, and outputs a number in this ideal. So it would be a global function on X with the exact property that it's only invertible there where we are in U. So a global section of J will exactly be a function f, like here, such that D of f is a subset of U. And what is this I lower star R? That is, again, a bundle. And at the point x, its fiber will be R to the truth value that x is an element of K. So in case that x actually is an element of K, this will just be R. In case x is not an element of K, this will be R to the empty set. So it will be the trivial R module, the zero module. And of course, I'm not claiming that these are the only options. And what does the map look like? The map maps a number A to a certain element in here, so to a certain function. And this function ignores its input and outputs A. Sometimes a map like this is also called a diagonal map. Okay. As soon as we pass to the third step, where we will take global sections, the meaning of those two bundles will get more clear. But first, I would like to convince you that this is surjective, fiber-wise. So, why is it fiber-wise surjective? For that, let an arbitrary x be given. Then we have two options. It might be that x is an element of U, or x is an element of V. And in both cases, we can conclude with two totally different reasons. Let's first do the case that x is an element of U. Then so in this case, the ideal is simply the unit ideal, contains everything. And this R to the x element K is then given by R to the truth value that those GIs vanish. So, by syntactic quasi-coherence, this is R mod the ideal GI of x. So that map here will simply be the canonical projection map from R to this particular quotient of R. And hence it will be surjective. In the other case, we argue differently. In the other case, the codomain will simply be the trivial R module. So in particular, that map will be surjective. Why is that? Well, if an element, if the point x is an element of V, then we know that it's not an element of K, because if it was an element of K, then it would also be an element of U, hence it would be an element of U intersected with V, hence it would be an element of the complement of K. To repeat it one more, if x is an element of V, then that truth value up here is simply bottom, then it is not the case that x is an element of K, because if x is an element of K, then it's also an element of U, hence an element of the intersection, hence it's not an element of K. That's the conclusion. Good. So we have this result on fiber-wise surjectivity.
Don't know if you talked about it, but in the same case distinction, you can also figure out that Jx is not actually a submodule of R. Maybe I just missed it. But I mean, we have to at least see it's a module.
Yeah, and Jx is always a submodule of R. I don't even need a case distinction for that. It doesn't hurt.
Yeah,
but I also, in very general situations where we are not in this specific context here with the covering, there we can always check that Jx is an idea.
And we don't have to check that it's WK.
Well, we need to, because now I will want to pass to global sections. And yeah, it is. So firstly, the codomain. That is WQC, because it's the push forward of a WQC bundle. And I think you proved that WQC bundles are stable under push forward. Not all kinds of properties of modules are stable under push forward, but WQC is. And why is JWQC? For that, I don't know a quick argument simply saying that it's a push forward of something. But you can just check it directly from the definition, or even quicker from that criterion for when an ideal is WQC. For that, you don't need to do arbitrary localizations. You just need to do the following. Let me just very quickly write it down, and then forget about
If
it.
we just use the case distinction and just check the case, Jx is R or J.
Could also be,
No, we don't know what it is.
Yeah, but in any case, it's nice to know that this is always WQC. The criterion is that as an ideal A in R is WQC if and only if for all F in R and for all X in R, if the assumption that F is invertible implies that X is an element in A, then X is actually an element of A after being multiplied with some power of F. And with that criterion, you can quickly check that this is WQC. Okay. Note, though this ideal is not obviously finitely generated. And that's also a part of the proof which especially David, I think, dislikes, because we are leaving the realm of everything is finite. It's still WQC, but it's no longer finite.
Did you ever compute the kernel?
Well, we can quickly do it in a second, but
Can also do it with the other.
yeah.
Because I mean, it would be enough to see that the kernel is double.
And that might be easier. You mean? Yes, good point. Good point, yeah. So let's conclude. The hardest part of the proof is over. because J and the codomain are pointwise WQC, and because we have that vanishing condition. The induced map on global sections is surjective. So what are these domain and codomain? That can be simplified a little bit. Let me quickly use type theory representation for that. This will be this type. The first pi is because of global sections on X, and the second pi is the definition of the push forward. And then we can also simplify this a little bit to this. So R to the K. So that's just the set of global functions on K. And we also already talked a little bit about the left-hand side. These will be all those functions on X such that d of f is a subset of D. And then we do the following. We observe that the codomain contains the constantly one function. Hence, there's a preimage. So there is a function f from X to R with d of f in U and with f restricted to K constantly 1. And I'm claiming that this function f will be the desired function f. It only remains to prove this covering condition. And that will be the final step of the proof. So let arbitrary point x be given. Then by assumption x is an element of U or of V. In the latter case, we are done. So we need to concentrate on the first case. Okay. We know that x is an element of U. We need to verify that f of x is non-zero. Or we need to verify that that x is an element of V. We already know that it's an element of U, so it's in either case it's an element of U intersected with V. So we have this description. Yeah, if this case holds, then we know that x is an element of d of f. And if one of these cases holds, then we know that x is an element of U intersected with V. So in particular, it will be an element of V. Okay, and for final step of the proof, we use the generalized field property. If we want to show that one of those numbers is non-zero, we just need to check that the assumption that they are all zero results in a contradiction. So if f of x and all those g's of x are zero, well, bless you, then x is an element of K because of these conditions. So f of x is surely 1 by this condition. But also it's 0. And that's it. So the idea of the proof in very high level terms is to use the assumption of cohomological triviality in order to construct suitable global functions. And this bundle morphism did not appear from nowhere. Instead, it was carefully chosen so as to be useful to that proof. J was chosen because we wanted to have this condition that d of f is an element of is a subset of U. And the quickest way to ensure that is to ensure from the very beginning that f will only be drawn from such a set. Yeah, and the codomain has been chosen to make this step in the proof work. As the final thing of today, I would like to just write down, as promised, the external interpretation of WQC. It's not directly related to that, but it will also be just one line, and then I'm done.
So the lemma needs much less than all WQC.
Right. It just needs that for a couple of particular WQC bundles. It needs it for the kernel of this bundle morphism. And recall, earlier there was also this time where we used the cohomological triviality condition in the proposition instead of in the lemma. And there we used it for the kernel of this matrix, of this horizontal matrix. With just a tiny bit more work, we can improve the assumption, weaken the assumption, so that it's not about all WQC bundles of modules, but just WQC bundles of ideals.
I think this is also what classically the formulation is.
That is also the classic formulation. That final step we need to do is also constructively fine. It's not a big deal. It's just a tiny bit of homological algebra. We just consider a certain filtration at some point and then notice that the subquotients of that filtration are all WQC ideals. Then we use it for that. And then by iteratively doing that, we then obtain the one vanishing condition for exactly that kernel of that horizontal matrix from before, and then we can continue as we learned it. So that's not the big deal. Okay, let me just write down this remark. Now set in an external context, not within SAG, let S be a base scheme. Let E in ZAR S be a module, an R module. R is the structure sheaf of the big Zariski topos. Then the following are equivalent. Firstly, the statement that E is WQC. And secondly, the following statement: for every scheme X over S, locally of finite presentation, and let's call that scheme of S and F. For every scheme like that, the OX module E, when restricted to the little Zariski topos of X, is quasi-coherent in the ordinary external sense of the word. Okay, and what's missing from full quasi-coherence is the following. Let me also write it down right now. Also, the following are equivalent. E is strongly quasi-coherent. And second, firstly, well, condition 2 from before. And then one further condition, namely the following. This one. So that's a quasi-coherent sheaf on S. And in algebraic geometry, I learned that I can pull back quasi-coherent sheaves. And the condition is that the canonical map, which we have here, is an isomorphism. So unlike WQC modules, strongly quasi-coherent modules always cannot shapeshift. Their shape is fixed. Their shape is governed by what they look like on S. The restriction to the little Zariski topos of S already completely determines E. The category of WQC modules in that sense is abelian. This category is also abelian. However, internally speaking, there will be a difference, because as soon as we are working internally, we are not actually referring to that or that category. Instead, we are referring to the fibered categories of those things, as in Nikos. And then it turns out that the fibered category of WQC modules is abelian in the fibered sense, so that kernels exist, but also they are stable under base change, under reindexing, while the fibered category of strongly quasi-coherent modules is not abelian in the fibered sense. Okay, that's it. Thank you very much for your attention. Any remaining questions?
It doesn't make sense to call strongly quasi-coherent modules then constant.
Yeah.
With the quasi-coherent modules.
Yeah.
So your contribution for strong quasi-coherent here, in the case where S in a Phi scheme is the K, it really just means a strong quasi-coherent module is the same as a K module.
You have an equivalence of categories between the external category of strongly quasi-coherent modules in that sense, and simply the category of quasi-coherent sheaves of OS modules in the traditional sense. And in the particular case that S is the spectrum of a ring, we obtain the category of all modules over that ring.
The weakly quasi-coherent modules which don't have the property below are those which have, like, I don't know, like chumps in the fiber so that the sections can't see the chumps.
Exactly. And a quick example where you nicely see those jumps is the following. Very short, very quick example. Due to the common room in Göteborg. Consider this linear map. Multiplication by 2. And then consider its kernel. Okay? The kernel will shift shape depending on whether in the current slice 2 happens to be invertible or not.
Yeah, I mean constant. Yeah,
Yeah.
So if you think of them as constant, then
yeah, it's not as constant as constant sheaf would be, but it's as constant as possible in a meaningful sense for
one
modules.
modules. Yeah.
Yeah, exactly.
Yeah. So I would propose them.
Yeah, I like the name. Yeah. But perhaps another name would be tethered, verankert. Tethered to the base, tethered from the base.
Yeah, but okay, but this is what we see externally. I mean, yeah, I'm not sure whether it makes sense.
Yeah.
But also the one where you have 0 everywhere and one line in the middle should also be not strongly quasi-frequent.
I agree.
In the middle of what? Everywhere in the middle?
So
in what space?
R to the x equals 0 or the other one?
Yeah.
So the lower.
Yeah, one of those, yeah.
Okay.
But the one of those will be WPC, right?
Yeah.
Okay.
R to the x equals 0.
Exactly. Okay, then let's.
I mean, global would be another name.
Yeah, that would also be a good name. Yeah. Again, it might be a little bit weird from an internal point of view, which doesn't know about global. Exactly in the same sense as the proposal of being tethered is a little bit weird.
Yeah.
Because the internal world doesn't know what should be the base it's tethered to. Yeah, but still, I also like it. Afterwards, we have coffee and all the remaining questions during the coffee break. The next talk will be by Ingo. Okay.
Yes.
Thank you again.